Swayam Prabha. Digital India. Educated India.
So in today's session, we will go over the idea of lift-induced drag. So in the previous sessions, we have gone over the other sources of drag, such as skin friction drag. Then we have talked about pressure drag due to flow separation. And we have also seen that in the high subsonic regime, where shock waves can form on locally on the wing, the aspect of wave drag shows up. Of course, in supersonic flight, wave drag is a common thing. In subsonic flights, we said that it occurs only at the high end of the subsonic Mach numbers, where where you have crossed the Mach critical for the wing or for the airfoil cross sections of the wing, and you have gone beyond the drag divergence Mach number, where a strong shock has formed on the surface of the wing, has caused flow separation, and then you have these large drag component that we have talked about, which we have labeled as wave drag. In today's session and in the follow-up session that we will have tomorrow, we are going to talk about this another very interesting component of drag, which you will see is known as lift-induced drag, and this is a drag component that is that arises because of two reasons. One is the finiteness of the wing. So when you go through these textbooks in aerodynamics, you will see that they talk about flow over airfoils or flow over infinite wings, and then there is a chapter called flow over finite wings, okay, or finite wing theory, elements of finite wing aerodynamics. So the finite wing term shows up, and so this finiteness of the wing, and also the fact that when a wing produces lift, there is a pressure difference between the upper surface and the lower surface of the wing. So what happens when you have a wing that is producing lift? So essentially that means that the pressure on the upper surface is lower than the pressure on the lower surface. That is why you get that net force in the in the direction perpendicular to the relative wind, which is the lift component. Because of this pressure differential and because of the finiteness of the wing, so there is a termination point. We call it the wing tip. So if you remember, the part of the wing that is attached to the fuselage is known as the root of the wing. The corresponding chord is known as the root chord. On the other hand, if you go away from the fuselage and come to the end of the wing, it's known as the tip of the wing. So what happens is when you have this pressure difference between the upper and the lower part of the wing, and you have these finite termination points, so essentially the wing tip, what will happen is the high pressure on the lower surface of the wing will have a way of pushing fluid to the upper surface of the wing because of the pressure differentials. Of course, if you have an infinite wing, there is no wing tip around which the high pressure can push flow to the low pressure surface of the wing, because there is no tip around which that thing can happen. However, when you have a finite wing, and then when you have a pressure difference, what will happen is around the tip, flow will move from the lower side to the upper side of the wing, so across the wing tips. When that will happen, this will lead to the generation of something known as the wingtip vortices. In fact, if you have seen pictures of contrails, so counter rotating vortex trails, you will see sometimes condensation occurs because of low pressures. So you will see that some the contrails become visible. So these trailing vortices become visible because of the condensation of moisture, and this has a far-reaching impact on the drag produced on the wing. Okay, so once again, if you are thinking of an infinite wing, we do not have the possibility of flow leaking from the lower high pressure to the upper low pressure surface. However, if you're looking at a finite wing, so around the wing tips where the pressure difference exists on the top and bottom surfaces, since the wing tip has a termination, flow can move around the wingtips on both sides, and superimposed on the flow that is coming towards the wing, you will have these contrails, counter rotating vortex trails that are shed from the tips of the wing. It will be seen that the Lanchester's model talks about the horseshoe vortex, supported by a wing. On the other hand, Prandtl's approach, which is considered as a more detailed approach, has vortex or vortices or vortex tubes um, being shed throughout the span of the wing. Okay, it is true that beyond a certain point, these small vortex tubes get sucked into a rolled. They roll up into these large contrails. So Lanchester's model and Prandtl's model have that similarity, that eventually you have these two contrails. But Lanchester developed this model based on that horseshoe vortex. We will see all these things, a little bit of introducing these few words ahead of time. So we will have this horseshoe vortex, and we will talk about what does it represent. In case of Prandtls, we don't just have two strong contrails. There are vortex tubes that are shed throughout the span, with the understanding that these continuously shed vortex tubes eventually uh, intertwine and generate those two large contrails as per the Lanchester's model. The analysis of Prandtl's model, however, assumes that these vortex tubes coming downstream or in the streamwise direction from the wing are they extend to infinity. But it's the model predicts some of these observed experimental data quite closely, and we will see those things in detail. So the study of these finite wing generated drag, which primarily is the wave, the induced drag, it essentially is lift induced drag. It occurs because of the finiteness and the pressure difference between the upper and lower surface of the wing, generating these vortices. In the Lanchester's model, vortices, you have two vortices at the wingtip. You have these vortex tubes from the wingtips. On the other hand, we will see that in Prandtl's model, the vortex tubes are not just from the wingtips, but the different spans of the wing. But however, they roll up into two large wingtip vortices eventually. These vortices, the shedding vortices from the wingtips, create something known as the induced velocity. So a big chunk of the study of these, lift-induced drag is to figure out the effect of these counter-rotating vortex trails on this induced velocity field at the wing. Okay, so you will see that it's known as the downwash, and depending on the way the lift is distributed on the wing, etc., and these shedding vortices, you will see that there is a way, something we use the Biosavert law to figure out what is the velocity field induced at the wing because of these shedding vortices, and then it can be shown that these induced velocity somehow modifies the relative wind direction, which modifies the it rotates or tilts the local lift vector, and that is essentially the source of the tilting of the local lift vector can be shown to create that induced drag. Okay, so whenever you have lift on a finite wing, you have induced drag, and we will see that this becomes a major component of the drag for these finite wings. Okay, so first I will kind of quickly go over the slides that I have for this particular topic. So first of all, a basic idea of the finite wing versus infinite wing. We have already talked about this. The fact that for a finite wing, we have these counter-rotating vortices shed from the wing tips. So okay, let me because this slide is not that easy to come back to. So let me just talk about what we have in this slide. So here we're talking about. So see, the moment we talk about incompressible flow, we are kind of excusing ourselves from the aspect of wave drag. Okay, so right now our focus is on incompressible flow over wings. Incompressible flow. When we say incompressible flow, we are not looking at wave drag aspect, because you remember that the waves show up when the compressible nature of the flow shows up, and this happens at high subsonic Mach numbers. Of course, it happens at supersonic Mach numbers. So whenever you see a vehicle flying at a very low Mach number, you can kind of think that wave drag perhaps is not, you know, a major contributor to the drag that the vehicle is experiencing. However, if your vehicle is flying at a decent Mach number, which you think or suspect is could be in the neighborhood of the critical Mach number, then you have to, take care of some of these aspects, the presence of wave drag. And if your vehicle is flying at, velocities or Mach numbers above 0.3, remember that is the compressibility range. Above Mach 0.3, compressibility comes in. You might do a better job if you do the CP corrections. So instead of using CP, it might be better for you to use CP is equal to CP naught by square root of 1 minus m infinity square, that Prandtl-Glauert's correction for compressibility. So these aspects, you have to keep in mind when you are given a problem, or when you face a problem. Your mind should quickly, run a differential diagnostics kind of thing, figure out, what is relevant, what is not relevant, or what is relatively more relevant, things like that. It might be argued that, everything is relevant. It is the relative importance of which one is more important. So right now we are saying, okay, let's look at the incompressible flow. So we are excusing ourselves from the wave drag component, and we are saying that incompressible flow, of course, it can happen over infinite wings, and infinite wings is essentially we are again excusing ourselves from whatever is happening at the tips. You understand that when a wing is infinite, we don't have a span-wise flow. Span-wise flow essentially. So this is the stream-wise flow. Okay, this direction is the stream-wise direction, and this direction is the span-wise direction. Okay, so this is the span-wise direction, whereas this one is the stream-wise direction. So for infinite wings, since we do not have the wing tips, the wing extends forever, and your airfoil cross section is fixed. So it's a given cross section, it extends to infinity. So there is no span-wise flow. Everything is just stream-wise. So if you take a cross section at any location of the wing, you will see exactly the same flow field. Okay, so for these 2D wings, if you run an experiment where you somehow prevent the span-wise flow, and one way to prevent span-wise flow is to take a finite wing of a fixed cross section and then put it in the wind tunnel so that the walls and the tips of that finite wing, they are flush mounted on each other. So there is no leakage flow. The moment you have that leakage from the lower surface to the upper surface, you have the finite wing effect. However, you can still take a finite wing of fixed cross section or fixed airfoil cross section, mount it in a wind tunnel such that there is no leakage. Okay, you can do it if your wing tips are flush mounted with the walls of the wind tunnel. So you can still take a finite wing, but yet collect data on it as if it is an infinite wing. Okay, so as long as you prevent the wingtip vortices from occurring, these wingtip vortices. However, if you have a small clearance between the walls of the wind tunnel and the tips of the wing, then the moment you are generating lift, there is a pressure difference, and then there is that gap through which the flow can leak, and you will have the trailing vortices, and that will create a span-wise component of flow. Okay, so that will make it flow over a finite wing behavior. So in a finite wing, because of these effects, because of this, the leakage of flow from this high pressure side to the low pressure side, you have a flow movement like this, which in turn influences the flow in the neighborhood, and it's a span-wise component of flow. Okay, so for the finite wing, you have to remember that we have a span-wise component of flow, whereas for an infinite wing, we just have stream-wise component. There is no span-wise. So flow over infinite wings was considered, when we, so whenever you have a, airfoil data, CL versus alpha, CD versus alpha, we also saw that sometimes CD versus CL and CL versus alpha both are given at the same time. Then CM, the moment coefficient, we have not talked too much about the moments on the airfoil. We will talk about them after we finish discussion on lift. You will see that the moments on the airfoil also. So when we talk about moment on the airfoil, we talk about moment on the airfoil, around the center of pressure or around the aerodynamic center. There are all these things around the leading edge, etc. But there we are getting data on that laboratory experiment where you are using a finite wing, but you have mounted it in such a way that it is mimicking what is required for an infinite wing. So from that you get 2D flow airfoil data, and it is only streamwise flow, as I said. On the other hand, flow over finite wings, essentially you allow these wingtip vortices. So for in a wind tunnel, you allow wingtip vortices by spacing out the wingtips from the wall, so you do not flush mount them. Flush mounting is like where the something touches something else in a very nice and gentle manner, or rather like there is no leakage or there is no protrusion. So flush mounting, you will hear this word many times. For example, when you put a bolt inside a wind tunnel, you touch the surface of the wind tunnel, but you don't feel the bolt protruding out or recessing in. So you say it's flush mounted. On the other hand, this perhaps flush mounting the wing is not the best word. What I'm trying to say is tightly fit. Okay, there is no leakage. On the other hand, if you are thinking of like airplanes in flight, of course you do not even need to worry about this flush mounting, or because if you have a vehicle in flight, of course you have wingtip and wingtip vortices, etc. So in case of this finite wing, you have both streamwise and spanwise flow. So this is an important concept. So this one is a finite wing. Okay, so we have the root chord, you have the tip chord, and when you have a pressure difference, flow from the lower surface moves to the upper surface, and in that manner, a vortex trail like this is created. That's what we see here and here. See, these are the trailing vortices. Now, so here also what is important to note is, so you have a free stream velocity. So vehicle is moving at a relative. So the vehicle is seeing a relative wind of v infinity. CR is the root chord. Now a few terms would be useful. This B is the wingspan. So you will often hear the thing that semi-span B by 2. Okay, so this is half of the span is B by 2. The whole wingspan is B. Now this is CR. This is C tip. So this is the tip chord. We will call it C. Okay, so the tip chord of the wing. You see that the flow on the top surface, because of the spanwise component of flow, so you have a flow which is going from the high pressure to the low pressure side in this manner. What happens is induces a velocity field, because of which when it is superimposed on this v infinity, the flow on the top surface of the wing kind of bends from the tip to the root. On the other hand, the flow on the lower surface of the wing bends from the root side to the tip side. So you can see that my flow is no longer simply streamwise as it would be for an infinite wing without any wingtip vortices. Here, these wingtip vortices are inducing a velocity field that is getting superimposed on the the overall streamwise component, and it's creating these local deflection of the flow field around the wing. Trailing vortices, and it is interesting to note that trailing vortices of a large aircraft, say a Boeing 747 or Airbus, the big Airbus 380, these trailing vortices can be powerful enough to cause small aircrafts flying too close to go out of control. Okay, so because you remember that a lot of these analyses are done with this V infinity, free stream, uniform free stream coming towards the vehicle. So relative wind is more or less like a uniform flow field. But if you are caught in the trailing vortex of a large aircraft flying in front of you, your control surfaces and many other things can go out of the design expectations. So when we design a vehicle, it is designed with some expectation. Our theories are developed on some expectation or assumptions. But if you expose a vehicle, say a small Cessna or a Piper Saratoga, that has taken off just behind, they call it the heavy, right? You following too close to 747 or a 380, then you can be caught up in these trailing vortices, and that can be quite catastrophic. So because of these, the timing and the spacing between aircrafts has to be well managed by the ATC. So here I have taken these image from Fundamentals of Aerodynamics by Professor Anderson. As I said, Professor Anderson was my professor while I was at the University of Maryland. And so, it is interesting because when we were students, we read a lot of books by Professor Anderson. And then to have him as your instructor of, so I had him for my compressible flow class, so high-speed aerodynamics, and later in my hypersonics class as well. So Professor Anderson taught us these two courses. And it is interesting that in one of the exams, he actually, in the hypersonics exam, we prepared for a lot of numericals and all these things. And then when we went to the exam hall, we saw that there were two questions. One was, write what do you know about hypersonic inviscid flows? Question one. And then question two was, write what you know about hypersonic viscid flows. And this is, I think, a part of the shift in philosophy between, the way different instructors, approach the learning of a course. So I think I have developed a way in between the two extremes. Um, so as you can see, I have some emphasis on the big picture, but again, I still focus on the details, and I try to include in the curriculums that we have in the classes. Of course, some numerical assignments are necessary, but I tend to believe that we have this. We try to delve into numericals too fast and too soon, and there is a problem to it, because if you start solving problems without really, getting a feel for the phenomenological description of processes, um, if you're able to solve the numericals, sometimes your mind gets, because you if you can solve a problem, you tend to believe that you have understood the phenomena. But oftentimes, we do not give enough attention or time to the phenomena itself. So I don't know. It's something called teaching philosophy. I think people should spend, at least you as students should spend time to understand first the phenomenological description. Okay, so what happens as a phenomena? And the good news is, for fluid mechanics and aerodynamics people, that after this YouTube came into existence, a lot of important organizations, starting from the universities all over the world, and National Aeronautics and Space Administration, as NASA as we know it popularly, and then even like many of our NAL, like National Aerospace Labs in Bangalore, they have put a lot of their experimental visualization work, etc., on YouTube. So if you search for trailing edge vortices on YouTube, you get a lot of real world trailing edge vortices on aircrafts, maybe rendered visible by colored dyes, or the condensation of water vapor in air. You will have a lot of visualization studies in wind tunnels. So I would strongly advise you to constantly get that phenomenological understanding, of at least the the feeling, phenomenological feeling of things. So because description in words or text is never enough. So when we were students, of course, that was our only recourse. Of course, I did my summer internship at NL Bangalore, that had a lot of important wind tunnels. But you cannot always run tests on demand. But your YouTube now is a beautiful source of these things, and I would strongly advise you. So for people who are in aerodynamics for the long haul, who want to go take it, like pursue research or get into industry as aerodynamicists, etc. So you should really see these things. The moment you see these things over and over again, your mind forms an opinion or an impression about what these phenomena are like, and then of course once you have a good idea about the phenomena, you can then apply your analysis. So coming back to this image on the top left, here you see, so you have smoke flow visualization on a wing cross section. As you can see, the wing is in a smoke tunnel. So wing is in a smoke tunnel, where individual stream tubes are made visible by smoke filaments. So what you do is you have a source of smoke. So you have a tube through which smoke is actually fed into the free stream. So you have these smoke lines, and they kind of render visible the stream tubes. So here you see that behind the wingtips, you see how the string tubes are intertwining into each other, which essentially is an effect of the trailing vortices. Okay, some of that's the Lanchester's model where you have these trailing vortices. In the Prandtl's model, you also have vortex tubes that are shed from at different locations from the span, of course, of various intensities, and then they eventually wrap up into these trailing vortices at a decent distance from the wing. When I say a decent distance, see, these are the expressions that are ambiguous, and they're ambiguous for a reason. So when we say decent distance or moderate distance, essentially you have to kind of, in experimental aerodynamics, you will say, okay, how many chord lengths behind the trailing edge does that happen? So if this is C, okay, so C, and you see this is a airfoil of constant cross section or fixed airfoil. So every cross section is a fixed airfoil. So CR and CT are the same. So you can just say C. So typically you will say 3C or 5C or 1C. Where do they get eventually wrapped up into this? So far field is still like this. The near field we will see. Sometimes you can have other small vortices being shed from the span as well, and you will see the reason for that. Okay, part of the reason is in the divergence-lessness of the vorticity field, but we will see what that is. At this point, I would also like to bring to your attention that this Karamchetty's book is a book that emphasizes on some of these fundamental aspects of the analytical aspects of vertical flows, etc. And for people who have an inclination for the mathematical way of dealing with or modeling things, you can actually look that up. I have some material from Karamchetty in this particular lecture, or rather this portion of the lecture on this lift-induced drag. But nonetheless, you see that on in the flow visualization study shown here on the top left, we have smoke lines, and you see that they are wrapping up into each other because of the counter rotating. So we say counter rotating because this one rotates in this manner. So the lower high pressure leaking onto the upper low pressure. On the other hand, here the lower high pressure leaking into the upper low pressure in this manner. So counter rotating. Okay, so the directions are different. So as I said, also sometimes in water tunnel, a lot of low speed studies can actually be performed in water tunnels. There, some of these visualizations can be rendered through hydrogen bubble visualization. So instead of a smoke generator, and also it's not always a smoke generator, you can also use a fog generator. There is called you can look it up on both the YouTube and Wikipedia or Google. It's like the generic Google search. So there's something called fog machine. And if you think of in some of those theatrical performances, in the dream sequences, right, they put smoke and fog and make it like very create the effect. And we sometimes use the same machine. It's called the fog machine. So smoke or fog, you can use these to render flow field visible, render air visible. If you are running these tests in water, you can use a colored dye. So you will have a tube with holes, and through that tube you can inject some colored dye at these different locations, and you can get a similar visualization. In NAL, actually, I saw these. Well, of course, I had read about it, but for the first time, I saw flow over a delta wing being rendered visible using colored dye in water. So they had a vertical water tunnel, and there was a delta wing vehicle. Of course, I think it was part of the LCA. At that time, India was getting started with the LCA design. Of course, it was not, some of these projects are not publicly disclosed, so I did not know what exactly was that for. But now, in retrospect or hindsight, I think that was flow visualization study on the wing for this LCA, light combat aircraft, that India has developed. And I saw for the first time how beautifully these vortices on a delta wing are being generated and demonstrated. Is water tunnel, colored dye, delta wing at an angle of attack. You have these very strong vortices on the upper surface of the wing, and it's a very strong tool to understand flow fields, and as I said, to get the phenomenological description of things, because only once you are clear about the phenomenological description, you can apply analysis and get somewhere. Okay, so as I also mentioned that, so you have now, so here we are modeling this wing by these horseshoe vortexes. So you see that when you have these trailing vortices, as you see on these both sides, it can be modeled by a vortex tube or a vortex filament with a circulation same as the circulation generated by these trailing vortices. Okay, so if you kind of look at the wing from from a location behind the wing, looking towards it, you will see that the circulation developed by these trailing vortices is something like this. So what you can do is, instead of dealing with this, the counter rotating vortex trails, you can model it by these vortex tubes. We will kind of I have a slide that talks about what is a vortex line, what is a vortex tube, what is a vortex filament. And here, essentially, these two lines, technically speaking, they are the vortex filaments. However, what is important is the strength of the filament is same as the strength of these contrails, which means that the circulation develops. So when we say strength of a vortex filament, we are essentially talking about the circulation. So circulation developed by the vortex filament. Circulation developed by the vortex filament or the vortex tube, etc. So here we are replacing these thing by these two vortex filaments whose circulations are same as the circulation developed by these contrails. Okay, that's how we model from the real to something that is more amenable to analytical description. Here, what we are saying is, now here we have in fact replaced the wing as well with the bound vortex. So we have not shown this, but here what you do is, the effect of the wing is really to generate a bound vortex. Of course, the strength of the bound vortex, if you remember, is such that the Kutta condition is obeyed. If you do not remember, just look up your notes from the Kelvin circulation theorem discussions. Okay, so while we were discussing Kelvin circulation theorem, we have talked about what is shedding vortex, what is bound vortex. Now, what is the strength of that bound vortex? We said that the strength is such that the flow does not leave the trailing edge abruptly. Okay, flow leaves the trailing edge smoothly, and that creates a measure of the bound vortex strength. So the effect of the wing is really to support a bound vortex, and when you have a bound vortex of a certain strength that kind of satisfies the Kutta condition, of course, when you have a vortex, you have circulation. Okay, now I'm saying that the strength of that circulation or strength of the bound vortex is a similar analogous terms. So strength of a vortex is given by the circulation developed by the vortex. So the strength of the vortex or the circulation developed by the vortex is such that for the wing, the flow leaves the trailing edge smoothly. Now, we have seen a little bit of this thing while we were discussing Kelvin circulation theorem. We will see this thing once again when we get into the study of lift, incompressible flow, inviscid incompressible irrotational flow fields. When we talk about lift generation in those flow fields, you will see that we will show how the flow over a spinning cylinder really creates that lift force. And then through something called the Zhukovsky transformation, we will show that a similar kind of lift force is generated on something that looks like an airfoil. Okay, so those things will come gradually. But at this point, what I'm trying to say is, so this is the physical description. Okay, you have a relative wind. You have the generation of trailing vortices. I said you can replace the trailing vortices with vortex filaments. As long as you can argue that the direction of the vortices are this way, and the strength of the vortex filament given by the circulation matches the circulation developed by these trailing vortices. So here we have replaced these two trailing vortices by these two vortex filaments. On the other hand, we can also replace the wing itself by a bound vortex line. So the red, the the flow direction or the vortex direction kind of signifies the bound vortex that is existing on the wing. Now, what is happening is, you see, we have said downwash distribution along the y-axis for a single horseshoe vortex. As I said, this is the Lanchester's model, where we just consider two trailing vortices and a bound vortex. However, we will see that if you see these small these vortex filaments, if you take those into consideration as well, then you get a distribution of horseshoe vortices. Okay, not a single horseshoe vortex, you get a sequence of horseshoe vortices. We will see this in the next slides. But at this point, let us look at the effect of a single horseshoe vortex. So you see that this trailing vortex generates circulation, or corresponds to a circulation developed by the the wingtip vortices, and this circulation influences the flow field. Almost every it actually influences the flow field everywhere. And in particular, if you now go to the wing location and you figure out what is the velocity field induced by these vortices, you can, so essentially, if you try to find what is the velocity field induced here, you have to work out the velocity field induced by this entire line vortex at this point, superimpose that with the velocity field imposed by this entire line vortex at this point, add them up, and it can be shown that the downwards distribution for a single horseshoe vortex looks something like this. Okay, so this is the downwash. So this is not the V infinity. So the net velocity that the wing will see will be locally will be a combination of V infinity and the downwash at that particular location, or at that particular span-wise location. So here you see, we said, so this is the span direction. So this is the stream-wise direction, and this is the span-wise direction. Okay. So total span is B, semi-span is B by 2. So see, it's from minus B by 2 to plus B by 2, and this is, you can think of it as the root chord location. So this is the downwash distribution, and we will see that the downwash distribution can vary from airfoil to airfoil. Actually, the downwash distribution will vary from airfoil to airfoil. So do not think that this is the characteristic downwash distribution. In fact, we will see that for elliptic lift distribution. Now you understand that a lot of I'm jumping a few things. What is the elliptic lift distribution? We have not talked about it, but at this point, just maybe it's a chicken egg problem. What something will come before something. So for elliptic lift distribution, and then the vortices that are shared, and then the induced velocity field, if you work it out, it surprisingly you will get a constant downwash. These are kind of quite counterintuitive things. That is, if your lift distribution is elliptic, and we will say what is this elliptic lift distribution in the subsequent slides. But if your lift distribution is elliptic, or then it can be shown that the vortices that are shared will set up a vorticity field or a circulation field, such that if you work out the velocities or the induced velocities at the wing, it actually comes uniform throughout the span. Okay, so span wise, it's a uniform downwash. However, for other lift distributions, non-elliptic lift distributions, your downwards distribution will change. Okay, it will not be uniform throughout the span. So once again, here you on the top left, you see an experimental verification of these counter-rotating vortices shed from the wingtips. Here I'm saying that given the direction of these vortex motion, you can create the direction of the vortex filament, and the strength of the vortex filament will be such that it matches the strength of these contrails. Strength meaning the circulation. Okay, circulation. I have a slide that revisits what is circulation, but by now you should know that circulation is defined as V dot dl over a closed path around which we are interested in to find the circulation, and it is also equal to, so that's in terms of velocity and the path. So you take a here or here you take a path around this vortex filament. Okay, you find what is V at every point, and you dot product it with the dl vector at every point, and you will get the circulation. So what we are saying is this circulation, and circulation around any particular plane here should match. Okay, if you are replacing that by this vortex filament. In terms of your vorticity, it can actually be shown that if eta is my vorticity, so essentially the vorticity multiplied by the surface over which it acts. So if you think of a cross section such as this, you have to multiply the vorticity by the cross section over which that vorticity acts. And of course, you take the component of surface, so essentially if your vorticity vectors are normal to the surface, then you just do, E dot, so EDS, just you take the magnitude and multiply by the area. Of course, if they have some mutual inclination, which is not aligned at 0 degrees to each other, then you have to take the component properly. Okay, so now, so a big story short, long story short, you have a finite wing generates trailing edge vortices. Trailing edge vortices can be replaced by trailing edge vortex filaments. The strength of the filament should match with the strength of the trailing vortex. We will see that the strength actually remains constant from cross section to cross section of this vortex filament. It's part of the Helmholtz, the vortex theorems. That is, at a given instant of time, your the strength of a vortex filament will be the same from location to location, and it stems from something which we mathematically say as the divergence less of the vorticity field. In fact, we will talk about it in the subsequent slides. This divergence less of the vorticity field is something that it needs to be understood to understand these vortex structures, the strength of the shed vortices. So the way you figure out the strength of these trailing vortex filaments across the span is it requires you to understand a bit of that Helmholtz vorticity theorem, where the strength. So if you have a vortex tube is nothing but a vortex filament of finite cross section. When you shrink it to infinite cross section, you think of it as a vortex filament. Often we use it in modeling, but in reality, you mostly have vortex tubes. Okay, so the cross section is so here it's a vortex filament. Cross section tends to 0, vorticity tends to infinity, but the circulation, so this thing stays the same as this thing. So in this case, you see that here my cross section. So if you think of a vortex tube, my cross section is not infinitesimal. My vorticity strength is also not infinite, and the product is of the vorticity and the cross section area is finite, so leading to a finite circulation. On the other hand, if you think of a vortex filament, you are shrinking the cross section of the vortex tube to infinitesimal. Your vorticity strength becomes infinite, but the product still stays the same. Okay, so that is how you think of a vortex filament. It's a vortex tube that you have shrunk to a line holding the strength or the circulation constant. Okay, so now this is just looking a little in detail about what we have just talked about in the previous slide. So this is the physical picture. This is replacing the contrails with vortex filaments. Again, the circulation strength is the same as the circulation strength here. Also, we will show how at any cross section, the circulation strength actually stays the same due to the divergence-lessness of the vorticity field. Of course, you can have a vortex filament of a certain strength breaking into two filaments. Then, there is a conservation of the strengths of these vortex filaments. And we will talk about how this happens, okay, in the subsequent slides. So once you have this, we said that you can figure out what is the downwash distribution because of the velocity field created by these circulation. Okay, so you have these vortex filaments and there is a circulation. This circulation creates a velocity field which actually produces a span-wise flow as well as a flow that is normal to the velocity vector. Okay, so you have a span-wise distribution of this W component, rather WZ, and the effect of these induced velocity is to eventually create a local velocity which is different from the global relative wind. Okay, so when the global relative wind is at V infinity, the local relative wind is a combination of V infinity and the local WZ. So your airfoil is actually seeing a V relative wind which is different from the V infinity. Okay, and you will see that this whole thing about VR, which is a combination of V infinity and W, is to tilt the lift vector locally by an angle which will be shown to be the source of the induced drag. Okay, so the tilting of the lift vector due to the induced velocity. Now, as I said that in the Prandtl's model, however, instead of these thinking of just to counter rotating contrails or vortex filaments, you have a distribution of vortex filaments of various strengths. We will see how you generate those strengths. Eventually, they roll up into vortex, these contrails. So near the wing, you still have a distribution of vortex filaments, unlike just two vortex filaments at the wing tips. So you have a distribution of vortex filaments along the span of the wing. But eventually, these vortex filaments influence the velocity field on each other, and there's I think it can be shown analytically or at least computationally that these things will actually wrap up into these large contrails eventually. Okay, so these vortex filaments will eventually get rolled up into these large vortex contrails, eventually giving the same description like this at a large distance. Now, how do we find the velocity field? So we said that, okay, a situation like this can be modeled as something like this. So this one is the bound vortex. So if you remember the bound vortex, the starting vortex, we talked about the, that Kelvin circulation theorem, that the circulation of this circuit remains unchanged if that elements in that circuit are experiencing, that inviscid, incompressible body force influence flow field. In some cases, this will also hold for compressible, but that you have the restriction of barotropic behavior. But nonetheless, we use that argument to say that the moment you have a starting vortex, you generate a bound vortex, and then so that was from Kelvin circulation theorem, and then also from the Kutta condition, which is observed experimentally, we said that the strength of the bound vortex will be such that it will make the flow leave the trailing edge smoothly. So that is the strength of the bound vortex we have here. The strength of the horseshoe vortex, I will hold on to that for the subsequent discussions. The strength of horseshoe vortex will of course depend on the strength of bound vortex and the way it is shed. Okay, if you have a continuous shedding throughout the span, if you just are using two contrails at the wingtips, the strengths have to be adjusted accordingly. Actually, the strengths are the same. Okay, so in this case, the horseshoe vortex strength is the same as the, and when I say strength, it essentially means the circulation. Okay, and if you want to find circulation, all you have to do is create a closed loop around these filaments, do the V dot dl. Okay, and that's how you calculate the strength. So here, so there is something known as the Biosavert law, and I think a lot of us have seen that during our study of electric fields. How the flow of current through a wire influences the electric field at a certain location, etc. Here we are using the Biosavert rule in finding the velocity field induced by the circulation. So you have a vortex filament. So this thing is a vortex filament. Of course, I have a slide on where you will kind of see what is a vortex line, what is a vortex tube, what is a vortex filament. But at this point, just waiting for what is in that slide. Let's still talk about this again. It's a vortex tube that is theoretically shrunk to zero cross section. So it's a vortex filament of given strength, this gamma, and then to find what is the velocity field induced at a point, say P. So I'm just using this nomenclature P. And in this particular case, the vortex filament extends from minus infinity to plus infinity. So this is the generic form. Okay, so what we do is the dv established at a location P due to a vortex filament of strength gamma can be given as gamma by 4 pi dl cross r. So dl is that small filament length vector, and r is the vector location of P with respect to that dl element. And you can get the dv as the proof of this is given in Karam-Chetty. So if some of you are interested in finding, so for those who are who are interested in this, you can consult Karam-Chetty's proof of this about Biosavert law. Once you know the dv established at location P due to the small element dl, you can of course integrate this from minus infinity to plus infinity because it's a infinite curved vortex filament. You can integrate it to get the overall velocity field induced at the location P by this vortex filament. Now you see that for these horseshoe vortex that we are seeing here, our vortex we are interested in finding the V at these locations due to these vortex filaments. So you see that this is known as the semi-infinite vortex filament, and this one is a straight vortex filament. Okay, so this one goes all the way. Goes all the way, eventually you actually close it up with the starting vortex line. But however, you can model it as semi-infinite from 0 to infinity. It depends on where your starting vortex is, but the effect of these elements on this gradually decrease as you go far away from this wing location. So mostly we will say that here, so this one was a curved vortex filament from minus infinity to plus infinity, and velocity induced at location P due to that. In this case here, we have a semi-infinite. So it starts from 0, goes to infinity, and it is a straight line vortex filament. Okay, it's a straight vortex filament. It's a semi-infinite straight line vortex filament. So here we are interested to find V at these locations, say at this location due to this semi-infinite vortex filament. So there we use this particular form. So A, you can think of A as, so this A to infinity is really your vortex filament of a given, circulation of a given strength. I should not even say given circulation strength. Strength of a vortex filament is really given by the circulation strength. So A infinity is really, say, you can think of this as A infinity. And then see at a right angle to this, you have a point P. So essentially we are talking about a point like this. So our interest is to see what is the velocity field induced at P due to this semi-infinite straight vortex filament. And that can be obtained simply by, like this is the general form and this is the specific form. And it can be shown that the velocity field induced by that semi-infinite straight vortex filament at the location P is the circulation strength, or the strength of the vortex filament divided by 4 pi times h, where h is the distance. So this is h. So essentially AP is h. The distance AP is h. So then at the location P, you can figure out what is the induced velocity. So this velocity is essentially induced by the horseshoe vortex filament here. Of course, here you have to add the effect of this as well. Okay, so what is V due to this? What is V at P due to this? You add them, and that's where you get the W at P, which is the induced velocity at the location P. So this is a very important first step in understanding this lift generated drag. Okay, so these these vortex filaments, because of the circulation structure they have, induce a velocity field, and you can calculate the velocity field using Biosavert law. This is the generic form of the Biosavert law, or some people also say Biot. I think Biot is the right pronunciation. I think if you look up on the internet, you will really find it for the electrical field problem. However, you can look up a Karam Chetty's book or one of these where this has been adapted to to the velocity field, and there is a lot of similar analogy between the electromagnetic field and the velocity field. For irrotational, that. Of course, I cannot just hand-wavingly say these things. There are some limitations under which a velocity field and the electromagnetic field can be modeled in similar mathematical manner. So I think that's the source of this idea that this Biosavert can be used for finding the velocity field induced at a location due to a vortex filament. Okay, so once you know what is the W induced here, you can obtain the W distribution. For example, for the downwards distribution along y-axis for a single horseshoe vortex. So this is a single horseshoe vortex. So this whatever I am drawing in red is that single horseshoe vortex. Okay, this red thing is the single horseshoe vortex, and of course you now know what this thing really represents. We start with the physical picture, replace the contrails with vortex filaments of same strength. That's the Lanchester's model. You can also think of the Prandtl's model, but we will come to a detailed discussion of the Prandtl's model, and you will see that it is known by the name of Prandtl's lifting line theory, etc. It's a very elegant way of analysis and showing how the lift induced drag can be obtained for finite wing. But at this point, I just want to draw your attention that once you know the strength of these trailing vortices by using the Biot-Savart law in some restricted form, we are not using the generalized form, because here our vortex filament goes from 0 to infinity, and the location of interest is at right angles to the 0 location, and there is a very nice closed form solution to finding V induced by the vortex filament at locations such as this. Of course, to find the net induced velocity at this, you have to look at the influence of this filament and this filament, and that way you can get the net W. This is the WZ. And then I said that when you vectorially add WZ to V infinity, okay, so you have the V infinity, which is the relative wind of the entire vehicle. Locally, at airfoil cross sections now for the finite wing, you have VR, which is a combination of these two. And it will be shown that the effect of VR will be to tilt the lift vector by an angle, which we will also see is called the induced angle, or induced angle of attack. And that will have an effect of tilting the lift vector by that angle. So a component of lift will come into play as the drag. So it is unfortunate that although we want lift, the moment you have lift, you have this lift induced drag, and it depends on the amount of downwash, and the amount of downwash also depends on the amount of lift. So this is a very strange situation, but nonetheless, it's what we will see in the corresponding lecture. So here in the next class, we will go over a little bit of details of the vorticity field and what is meant by divergence less of the vorticity field, and how it leads to the the Helmholtz vorticity rules. Here we will just quickly go through what is circulation, what is vorticity. I think we have seen this once, so I will not spend too much time on this. And then this is the connection between the angular velocity of fluid parcels and vorticity. This will help you to understand the direction of the vortex filament in that trailing vortices. Okay. So here a little bit about what is vortex line, what is vortex surface, vortex tube, vortex filament, and so this one is where we will understand how that Kelvin's vorticity theorems are happen, and then here we will see that how the conservation of the strength of the vortex filament happens, and how the shed vortex filament strengths can be obtained. So once you understand the divergence-less and then the conservation of the strength of vortex tube, then from that we will be able to figure out some of these aspects. So okay, so thank you for this, for being present for this lecture, and then we will continue our discussion on this lift induced drag in the next class.